In this video, we will introduce the chi-square test of proportions. The chi-square test of proportions is very useful when we have qualitative variables, or otherwise known as categorical variables, because the only thing we can compare when we have categories measured at the nominal or ordinal level is to compare their proportions. This test examines whether proportions of different categories are unequal. That is, it tests whether the observed proportions are inconsistent with random sampling from a population with equal proportions. The first thing we need is an index of proportion inequality. We need to be able to calculate something that will be 0 when there are equal proportions and will grow as proportions become more and more unequal. We will need to know the sampling distribution of this index. That is, the distribution of values for this index when samples are drawn from a population where there are equal proportions. And our hypothesis testing procedure will then direct us to calculate the probability of obtaining a proportion like the one we observed by sampling from a population where the actual proportions are equal, and evaluating the unexpectedness of this probability in comparison to a set criterion, that is our alpha level. So this is how we go about checking whether there are differences in proportions when we have categorical variables. We will start with a single variable in order to introduce the concept, the distribution, and the procedure. In a later video, we will apply that to pairs of variables in order to be able to say something about their relationship. Let us start with a very simple example. Our beloved sex variable. We just stand outside a high school and write down the sex of each person we see going in. We assume these are all students, and we write down if there's a man or a woman going in. And we do this for 60 people. From a methods perspective, this is a horrible idea. This is a convenient sample of the worst form. But from a statistics perspective, it just counts. So let's just say we sit outside the high school, we write down how many men and women go in for 60 persons, and it turns out we write down 36 men and 24 women. This is our observation. So we've observed more men to go in than women. Can we conclude that there are more men than women in this high school? Can we generalize to the relevant population? I'm asking this from a statistics viewpoint, not from a methods viewpoint. So let's ignore the sampling problem now and just look at the proportions. Is 36 versus 24 sufficient evidence to say that there are probably more men than women in this high school in general? This is the question. So is there evidence that the population, that is the students in this high school, have unequal proportions of men and women? The first thing we do when we have any question of this sort is to hypothesize that there is no difference. That's our beloved null hypothesis. So I hypothesize no difference. This means equal proportions. No difference in proportions means equal proportions. So our null hypothesis is that there are equal numbers of men and women in this high school, 50-50. If there are equal proportions, then the expected numbers for a sample of size 60 would be 30 men and 30 women. That's equal proportions. Instead, we got 36 men and 24 women. How can we quantify this deviation from the expected numbers? What we have to do is we have to calculate an index of inequality based on the observed distances from the expectation of equality. Let's see how that's done. The first thing we have is our observation. So the observed counts are 36 men and 24 women. So that's 60 people. And our expectation from the null hypothesis of even proportions would be 30 men and 30 women, so equal. This is the expected count from the null hypothesis of equal proportions. How far are we from the expectation? We can just subtract these, subtract the expected from the observed, and we get these differences. Now, obviously, if we have an excess of observed men, this number will be equal to how many fewer women we have observed. So the sum of all these deviations from expectation will have to be 0. This is a familiar situation. So we can't really add up all the deviations to have an index of how far from expectation we are. What do we do when we have unwanted negative numbers that add up to 0 with all the corresponding positive numbers? We use our mathematical trick of multiplying these numbers by themselves. So raising them to the second power. In this way, both become equal to 36. Now, these are our squared deviations from expectation. This would be a reasonable index of deviation from expectation. However, we miss something important. Note that these numbers we get here are of the same order of magnitude as the observations. So they're fairly substantial. If you look at the actual deviations, we have a deviation that is 1/5 of the expectation. So we expected 30 and we got 6 more or 6 less. That is a whole 20% deviation. But this isn't really seen in these numbers. Imagine we had observed 600 students. Imagine we had observed 306 men and 294 women instead. Now, the expectation for 600 would have been equal, so 300 each. So again, there's a deviation of 6 in each case, and a square deviation of 36. But now, this deviation seems really small in comparison to the expectation. Indeed, these two numbers, the observed counts, look fairly similar. These numbers don't look so similar because the relative proportions of the deviations are very different. So here we only have a 2% deviation from expectation. Here we have a 20%. This needs to be reflected somewhere in our index of inequality. So what we can do is we can divide the square differences that we have calculated by the expectation, by the expected values. So then we have a relative square deviation instead of an absolute square deviation. If we do that, we get 1.2 in our example. So 36 divided by 30 is 1.2, amounting to a 20% difference. But 36 divided over 300 would only be 0.12. So that's a much smaller relative squared deviation. And this expresses the intuitive sense that these aren't as different as these. So after we've divided each square deviation by the corresponding expectation, so this divided by this, and this divided by this, then we end up with these numbers, and then we just add them up. We add up all these relative square deviations, and if we want to display this with a formula, it's this one. This formula indicates what we just did. We subtracted the expectation from each corresponding observation, then raised the differences to the second power, just multiplied them by themselves, divided by the corresponding expectation, and then added them up. And that has happened for k categories. So now we have two categories. K is equal to 2. So we've done this twice before adding, and the sum of these two values is 2.4. And this quantity is called a chi-square. So that's it. That's how you calculate a chi-square index of inequality. The value we got is 2.4. Now we need to know how unexpected 2.4 is if we're sampling from a population with even proportions. That is the null hypothesis. What we need, in other words, is the sampling distribution of chi-square. To do that, we can sample many times from a simulated population with equal proportions and just go through the same sequence. So we just draw 60 individuals from a simulated population with equal proportions of men and women. For each one of these samples of 60, we note the counts for men and women, and then the expected is always 30. We subtract, square, divide, add up, and come up with a chi-square for each sample. And we can do that 10,000 times. This is a familiar operation. Indeed, in this case, it's very much like flipping a coin 60 times and counting heads and tails. However, instead of going through the binomial distribution to evaluate that, we calculate a chi-square because a chi-square is extensible to more categories and more variables. And this is why we're learning it through this example. So what is the sampling distribution? If we simulate 10,000 samples in this way, drawn from population with equal proportions, and calculate chi-squares, we get this histogram of chi-square values. These are the actual chi-square values in a histogram that we've derived from 10,000 samples. And as it turns out, this has already been worked out mathematically, and there is a theoretical curve to which our samples conform. So this is the mathematical curve that we just matched with our simulation. We don't need to do these simulations all the time because we know this curve. The mathematicians have provided that for us. And this is the chi-square curve for two categories. And if we look up the value that we observed, which was 2.4, remember we calculated a chi-square of 2.4. It turns out that the probability of obtaining a chi-square of 2.4 or greater in this curve is 12.1%. So, in other words, the probability of obtaining a chi-square greater than or equal to 2.4 in samples of size 60 drawn from populations with even proportions of two categories is 12.1%. This is our p-value. Our p-value is 0.12. Is our p-value low? It's not very low. It's well above the conventional criterion of 5%. Therefore, we cannot reject the null hypothesis. The difference in proportions that we observed, the fact that we noted down 36 men and only 24 women, this observed difference in proportions is not statistically significant. This means that our finding, our observation, is consistent with random sampling from a population of high school students with equal proportions of the two sexes. So if we are sampling from a population with equal proportions, it's not too unexpected to get 36 in one category and 24 in the other. It will happen up to 12% of the time. In other words, the observed proportion is not statistically distinguishable from equal proportions. It's important to remember that sample size always matters. So the evidence for a given proportion has different weight depending on the size of the sample. If we had sampled 600 students and got the same proportion as before, but now with larger numbers, so 360 men versus 240 women. So just multiply everything by 10. So same proportions, but sample size 10 times larger. What are the values and what's the chi-square if we do the same thing? The expected values would be 300 now. The differences are 60 squared to 3,600 divided by the expected, added up. Our chi-square in this case would have been 24. If we have a 10 times larger sample size, we end up with a 10 times larger chi-square for two categories in this case. 24 isn't even on the graph. The axis goes only up to 12 here because the probability has already gone so low that we're not showing it. If we ask a program to calculate this for us, it turns out that the probability of getting 24 or higher is this number. That's an E minus 7. So you need 6 zeros to the left of 9. In other words, the probability here of obtaining a chi-square greater than or equal to 24 in samples of size 600 drawn from populations with even proportions of two categories is this number. This is a very low p-value. It means it is extremely unlikely to draw 360 or more men if you're drawing from a population with equal proportions of men and women. In other words, we have to reject the null hypothesis of equal proportions and say that our finding, our difference in proportions that we observed is statistically significant. In other words, our finding is not consistent with random sampling from a population of high school students with equal proportions of the two sexes in this second case, or that the observed proportion is statistically distinguishable from equal proportions. So it's not just the proportions that are important, it's also the sample size that is very important. What if there are more than two categories? How does this procedure work? Let's use a different example, this time with real numbers. The number of second-year students in each track of studies in the Norwegian Master's Program here in the Department of Special Needs Education in the fall of 2020 was given by the administration as these numbers. It looks like there are more students enrolled in some tracks than in other tracks. So some tracks are close to 20 and some are close to 30. Is this consistent with sampling from equal proportions, or is this evidence for different preferences in the relevant population, the population of students or the population of applicants to these programs? Let's calculate a chi-square index to find out if these observed counts are consistent with sampling from equal proportions. We're going to form the same table. These are our 5 study tracks, and the observed counts are here. The total number of students is 123, just adding all these up. So, assuming equal proportions, the expected counts would have been 123 divided by the number of categories, which is 5, and that's 23.6. Of course, you can have a decimal number of students in any track, but this is the math that we have to do now. So the calculations require that we use the expected value as derived from this division. So you're going to use this number for every track as the expected count. The difference from expectation, therefore, is subtracting this minus this, and this is the result. Subtracting this minus this, and this is the result. This minus this, and so on. So always observed minus expected. The sum of all these would, of course, be equal to 0. So we multiply them by themselves, and we obtain these numbers. And then we divide each number by the corresponding expectation. So divide this by the expectation. We divide this by the expectation. This one by the corresponding expectation, and so on. And these are the results. And then we just add all these up. And our chi-square, which is the result of this formula, which is what we've just done, add them up, and we get 2.163. What is the sampling distribution for a chi-square when there are 5 categories? We can again simulate a population with equal proportions of 5 categories and draw samples of 123 from that population, which is our null hypothesis, and calculate the chi-square for each one of them. That will give us the sampling distribution for this index. So the null hypothesis of equal proportions amounts to an imaginary population with equal proportions of 5 categories. We draw 10,000 samples in a simulation, we calculate the chi-square indices for each one of them, and this is what we get. Notice this is a very different shape than the one we got before with just 2 categories. These are actual simulation results. The mathematical curve that corresponds to 5 categories is this one. And here you can see it without the histogram from the simulation, just the theoretical curve. If we look up our value, the observed value of 2.16, then we find that the probability of a value as large or greater than this one in this distribution is more than 70%. In other words, the probability of obtaining a chi-square value greater than or equal to the observed value of 2.16 in samples of size 123 drawn from a simulated population with equal proportions of 5 different categories is 70.6%. So that's 0.7. That is a very large probability, and it's certainly not a statistically significant difference in proportions. the null hypothesis is not rejected. It is in fact quite expected to find differences in proportions such as the ones observed in this student sample if we assume that there aren't any differences in proportions in the relevant population. So our observations are consistent with random sampling from a population of master students with equal proportions in the study tracks, in the 5 study tracks, or that the observed proportion is not statistically distinguishable from equal proportions. So we have no evidence for special preferences in any of the tracks, given the current observations for students in this year. The fact that the curves for 2 categories and 5 categories were so different has to do with the idea of degrees of freedom. What are degrees of freedom? Why are the curves so different? The easiest way to think about degrees of freedom is, just as the word says, how many of the observed values of our variables are free to vary without affecting the total. The total cannot be affected because it's our sample size. So if we have observed 36 men and 24 women, that's 60 people in total. This total is fixed because it's our sample size. We need the sample size to calculate the expectation. However, we can imagine a different observation with the same expectation. If there had been 35 men, then keeping the total of 60, there should have been 25 women. If there had been 40 men, then there should be 20 women. That's how you retain the total. So one of these 2 values is free to vary, either one, but if one varies, the other one must compensate. So the second value is not free because it's constrained by the total. Therefore, when you have 2 categories, and because only one of the 2 can vary, there is only 1 degree of freedom. So 2 categories, 1 degree of freedom. In the second example, where we had these numbers of students, and the total was 123, this is what cannot change. Now, how many of these values can vary while the total can remain 123? Imagine that there were 22 students in this track, so 1 more, 29 in this one, again 1 more, 30 in this one, again 1 more, 23 in this one, again 1 more. So we've changed 4 of them, and now this one has to be 19 in order for the total to remain 123. So we can change up to 4 of these, any 4, but the 5th one must compensate to keep the sum total unchanged. So when you have 5 values, there are 4 degrees of freedom because up to 4 values are free to vary while the sum can remain fixed. In general, the number of degrees of freedom is equal to 1 less than the number of categories. So if there are k categories, the degrees of freedom, df, is how we write degrees of freedom in shorthand. The abbreviation of degrees of freedom is df, and that equals the number of categories minus 1. And that's for the simple chi-square test of proportions on 1 variable with k categories. We'll see later how that works when we have more variables. And to have a visual representation of the differences, this is the curve for 1 degree of freedom. So this is the curve we had before with the 2 categories. This is the curve for 2 degrees of freedom. That is when there are 3 different categories. The curve for 3 degrees of freedom. So 4 categories. You see this is a rather different shape. And then for more degrees of freedom, it's variations on this shape that just tends to get wider and a bit shifted to the right and a bit lower. This curve here is the one we used with the 5 categories, 4 degrees of freedom. So these are the sampling distributions of chi-square with different degrees of freedom from 1 to 6. And these are the sampling distributions according to which we evaluate the probability of the index we derive from our observed counts.